After starting and taking some essential outputs, it's time to explore the performance control of the GE90 engine. Modern-day jet engines are built to work on a system called the Full Authority Digital Engine Control. Except for few engine control, everything else lies in the hands of a complex closed-loop system, involving sensors, computers, actuation mechanism, and feedback systems. The engine has a wide operating range, and optimizing the engine performance at every lever setting is critical. We'll see exactly how it's done in this performance video. The performance of the engine is monitored and controlled by the electronic engine control. The EEC for its performance calculation collects data from several sensors. Let's look at the sensors installed on the engine. The N1 speed sensor is located on the core case and directly measures the N1 shaft RPM. The N2 speed sensor measures the engine gearbox speed to determine the N2 RPM. As the gearbox is driven by the N2 shaft, their speed is directly proportional. Temperature probes on the engine provide the EEC with temperature data of various sections. Inlet air temperature entering the engine. Temperature of the air entering the high-pressure compressor stage. Air temperature before it enters the combustion chamber. And the temperature of the exhaust gas vacating the engine. In addition to temperature, the EEC also calculates pressure, with the help of 4 pneumatic ports. The HP bleed duct pressure, combustion inlet pressure, LPC exit pressure, and the ambient pressure surrounding the engine. The compressor and the turbine sections are designed to work at their peak efficiency, when the engine is near its maximum thrust rating. The airflow and the blade performance is optimal at the design point. But it's not possible to use the engine at its max rating at all times. Currently the engine is at part power, and it can further go down to idle. Going through such extensive changes is exactly where the performance of the engine takes a hit. To counter this, the GE90 is equipped with 4 crucial systems that controls the airflow into the low-pressure compressor, the high-pressure compressor, the high-pressure turbine, and the low-pressure turbine for all thrust settings. Let's start with the variable bleed valve system. When the engine is at low power setting, the amount of airflow that exits the low-pressure compressor stage is far greater than what the high-pressure compressor stage can handle. The HPC's inability to accept the excess airflow overloads the low-pressure compressor stages, which drops their efficiency and compromises the stall margin. If not rectified, the LPCs can experience a compressor stall and lead to abrupt engine failure. Recognizing this, the EEC commands the hydromechanical unit to operate the variable bleed system. The HMU, apart from controlling the fuel for combustion, also controls the servo fuel system of the engine. It uses servo fuel pressure to operate the 2 VBV actuators. The actuators, with the help of bell crank and unison ring, controls the 10 bleed valves located behind the LPC casing. The valves now open to let part of the LPC exit airflow to pass through ducts and into the engine bypass airstream. This helps to match the LPC exit flow to the HPC intake, thereby reducing the load on the low-pressure compressors. LVDTs on the actuators give the actuator position signal to the EEC. The feedback helps the EEC control the bleed valves with precision. As the speed of the engine is increased, the valves are gradually commanded to a more closed position, increasing the airflow into the HPC stages. The variable stator vanes supplements the VBV system in increasing the compressor efficiency at low speeds. The VSV system controls the airflow in the high-pressure compressor by controlling 5 stages. Inlet guide vanes, first, second, third, and fourth stator stages. Compressors are unstable at low engine speeds, and the stator vanes experience flow separation at their trailing edges. If the vane's angle of incidence is higher, then the separation increases, resulting in breakdown of airflow, which the subsequent rotor blade finds hard to accelerate. Pockets of such inefficiently compressed stall cells starts to form throughout the compressor stages, thereby reducing the efficiency of the high-pressure compressors. Poor performance of HPC stages overloads the low-pressure compressors due to airflow mismatch, which can lead to compressor surging and eventually engine damage. To prevent this, the EEC commands the HMU to operate the variable stator vane. The HMU now sends pressurized fuel to the VSV actuators. Two VSV actuators on either side of the engine controls the torsion rods. The torsion rods are connected to 5 unison rings on the HPC casing. The unison rings with linkages turns the IGV and stator vanes of the HPC stages, reducing the angle of incidence of the stator vanes to improve the airflow into the HPC and eliminate stall cell formation. The VSV system ensures the compressor at low speeds continues to work within the stall margin. Feedback signal helps the EEC to calculate the real-time stator vane position. And as the speed of the engine is increased, the vane's angle of incidence is increased to a more open position, since the HPC is now in its performance zone with high rotational speed. Running the engine at higher speed means more fuel is burned in the combustion chamber, which increases the temperature in the turbine and the exhaust sections. Exhaust gas temperature on the GE90 can reach 1000 degrees. The high temperature causes the turbine section casing to experience thermal expansion. The expansion increases the tip clearance between the turbine rotor blades and the casing. A significant amount of combustion gas forces now vacate the turbine section without hitting the rotor blades. This results in loss of energy, and the engine has to burn more fuel to reach the desired power. To comparatively burn less fuel and get maximum efficiency, the clearance needs to be as less as possible, so that majority of the gas forces transfer their energy onto the turbine blades. Let's look at the two systems that help the engine achieve minimum tip clearance. High pressure turbine, active clearance control. The EEC commands the HMU to send servo fuel pressure to the HPT-ACC valve. The valve opens to let the engine bypass air to pass through a duct, and onto the manifold, around the high-pressure turbine casing. Low-pressure turbine, active clearance control. The LPT-ACC system uses a different actuation mechanism. Instead of the servo fuel pressure from the HMU, it takes a pneumatic line from the HPC stages. The electro-pneumatic valve is directly controlled by the EEC. The valve opens to let the bypass air to reach the manifold around the LPT turbine casing. The circulation in the manifold cools the turbine casing, reducing their temperature and thereby decreases the thermal expansion. This keeps the tip clearance to a minimum, giving higher power for the fuel burn. Both the valves give their position feedback to the EEC. Reducing the engine speed drops the temperature in the turbine section, therefore the valves are moved to a more closed position, but are never fully closed, ensuring limited airflow continues to cool the casing at idle speed. In the fourth installment of the GE90 engine series, we'll learn about the engine protection systems. Thanks for watching.